let's dive right in. So let's start with why do we care about visual quality? I'm pretty sure every single graphics practitioner in this room at some point in their projects had come across a situation where they had to trade off between performance and quality. It could be situations like rendering your optimizer. Let's say there's a limit on number of pixels you can shade. So you have to find out which pixels to shade and which not to, so that your visual quality remains pristine. Or it could be a situation where you are streaming your games over internet, and due to various circumstances like changing server loads or changing bandwidth, you might have to throw away some data packets. Now the question is which data packets to throw away. Um, Again, to retain the visual quality. And more recently, it's becoming a trend that more and more pixels are just AI generated and not rendered. And in those situations, it's super important to ensure that the hallucinated pixels match the targeted intended quality. Visual quality has become the currency you spend to gain speed, compression, or power savings. And sometimes you overpay, sometimes you underspend. A good metric helps you budget wisely. So now that we have established that visual quality is important, how do we quantify it? How do we measure it? The golden standard is to just have a human look at the video. You will get exactly how you will perceive your rendering technology. But of course, this is not scalable. It's expensive. Human time is expensive. Humans are slow, and it's very hard to recreate their responses across different lab conditions. A very common alternative to user studies is image quality metrics. And yesterday, we saw a lot of PSNR and SSIM scores in different talks. And there's beauty to that. It's very simple. It's computationally efficient, and it's reproducible. But they suffer from an obvious problem that they don't model temporal artifacts. OK, let's see if this artifact is visible here. So the first two images look almost identical. They only differ slightly in terms of brightness. And image quality metrics would say there's no error between the between the two images, because they are slightly different. But when the same two images are played consecutively in a video, suddenly the error becomes visible as annoying flicker. It's not super visible due to the projector washing it out, but take my word for it. OK, so we need to model temporal artifacts. There are video quality metrics for this purpose. Some common examples are VMAF, STIRRED, or all sorts of video visible difference predictors. And they do model temporal artifacts. But they have one major problem. All of them were designed for streaming use cases, for example, Netflix, VMAF, or color video VDP. And they are designed for natural content and compression artifacts, which can be very different from graphics artifacts. All the modern rendering techniques leads to artifacts which are very different in statistics than compression artifacts. For example, neural upscalers can lead to ghosting if the motion is not tracked very well. And path tracing methods can lead to shimmering and high-frequency noise. Aliasing and flicker, I'm sure everyone's quite familiar with them. And more recently, you get weird sorts of hallucinations in view synthesis methods, and it's hard to even describe them with words like aliasing or flicker. These artifacts are spatial and temporal in nature, and they do not resemble compression artifacts, which are blocky kind of in nature. And existing metrics are not tuned for these artifacts, so naturally they do not work very well for computer graphics distortions. A sentiment that is kind of resonated in this room. So there's clearly a gap. There is no data set with realistic rendering artifacts and human ratings on those artifacts. And there is no metric that has been tuned for real-time rendering distortions. So we introduced two key contributions. One is a dataset, CGVQD. It contains rendering-specific distortions and their human ratings for a wide variety of scenes and rendering techniques. And CGVQM, it's a full reference video quality metric based on pre-trained 3D CNNs. And it is seen to perform in the next few slides that it works really well for graphics datasets and traditional datasets too. Let's dive into the data set first. Like I described earlier, existing data sets like from the live group or VCAG group, again, focus mostly on natural scenes and compression noise. Um, and when I surveyed all the data sets and metrics 2 years ago, about 132 papers, 124 of them were on natural content, and only 8 of them were on consisted of video game videos. And even then, they only focused on compression artifacts. Um, so what's missing is we want artifacts from neural rendering methods, part tracing methods, view synthesis methods, which is something people in this room are interested in. And we want those artifacts on synthetic scenes, which are representative of modern video games. Here's a quick overview of the data set. It consists of 80 video sequences, 3 seconds each, made from 14 high-quality scenes, which we took from Unreal, Unity, and some open-source scenes from NVIDIA, Intel, and Amazon. We use 6 modern rendering techniques. I'll describe them in a moment. And we ran a user study with 20 participants and collected their mean opinion score. Here are the 14 scenes we used in our study. They are, again, some of the scenes that have been popularly used for game engine demos, like Infiltrator, Meerkat, or Zero Day. And we also added some custom scenes which kind of invokes edge case scenarios, like very fine geometry, bright lights, which leads to ghosting, complex materials, and diverse sorts of motion characteristics. Here are the 6 rendering techniques we used for in our data set. We used neural partitioning pyramids for neural denoising. We used XCSS for neural supersampling, just vanilla path tracing, Gaussian splatting, NVIDIA frame rate up conversion for video interpolation, and Alzar for variable rate shading. And the kind of artifacts we get from these techniques include examples of, let's say, over-smoothing in denoisers. And then we have ghosting, aliasing, and flicker in upsampling, warping artifacts and video interpolation, shimmering and path tracing, kind of texture blocking and variable rate shading, and blurriness and hallucinations and Gaussian splatting. In addition to just rendering these scenes, we rendered them at 4 to 5 different levels of complexity, different levels of quality, to ensure that it contains a mix of almost invisible distortions, barely visible distortions, and clearly visible distortions, modeling the kind of scenarios you often come against in real life. The study protocol was direct rating method. Basically, the study was conducted remotely, and everyone saw 80 videos in random order, and they were played in a loop, and everyone was asked to flip between the distorted video and its corresponding reference version, and rate the video on a scale of very annoying to imperceptible in terms of quality of distortions. Each participant rated each video 3 times, giving us 240 ratings per participant. And the raw ratings were converted to average DMOS scores using Surreal Toolbox, which lets you do outlier rejection and Z normalization. And since it was remote study, we did not have control over viewing conditions. We ensured that all participants had expertise in graphics, and we ensured they tried to simulate situations of PC gaming, how they would play a video game on their display. So here are the key observations from the user study. The first one is that the quality of a rendering technique or a scene does not scale linearly with different parameters of the rendering technique. So just tuning the parameters can maybe not have any effect on the visual quality or can have a huge effect. And also, for example, let's say flicker is visible on one scene due to one technique, it might not be visible in a different scene from the same technique. It's highly content dependent. You can see wide variety of curves across different scenes here. Also, some of the distortions were nearly imperceptible. For example, in the path tracing of jungle scene, for 256 SPP and 64 samples per pixel, they're almost the reference quality. even though if you take the pixel difference between the two videos, you will notice there is errors, which is super important point because this kind of highlights that mathematical error is not same as perceptual error, and we should be using perceptual metrics for determining quality of a video. Another interesting observation, which is very different from the compression papers I've been reading earlier, is that the results were not always monotonic with the decreasing levels of distortions. It is interesting, which basically says that just throwing more and more compute to your methods may not improve the quality, and maybe, in some cases, even make it slightly worse. And finally, this is like a quantification of all the anecdotes I heard yesterday that existing quality metrics do not perform well on computer graphics distortions. So you would expect a human-level metric to have a Pearson correlation of up to 0.96, but the best score we got was 0.78 from HAR-PSI, and even more popular metrics like SSIM, DIST, LPIPS, and PSNR performed even worse. There's clearly a gap between the best performing metric and human, and we want to fill this gap. So let's build a metric that fills this gap. Introducing computer graphics video quality metric. So how do we build a metric? So since we are trying to mimic how humans perceive quality, let's understand how humans come to a decision about quantifying quality for an image or a video. So the way it works is when we look at a screen, just pixel representation of an image, we map that pixel representation through our visual system into some neural representation. And this neural representation is what we end up using to do high-level tasks like rating quality of an image or comparing two images. So what we need as a first step of building this metric is a mapping function that maps from pixel space to some sort of a proxy of this neural representation. And we have multiple choices, multiple approaches towards this mapping function. Usually this can be categorized into three broad categories: psychophysical metrics, handcrafted visual features, or D-feature spaces. Psychophysical metrics, they kind of build upon simple visual models like contrast sensitivity or contrast masking that have been built using user studies on very simple patterns like sine waves or Gaussian patterns. And we try to extend them to complex images. They are amazing at extrapolating to different viewing conditions, but they struggle with modeling higher order vision like motion. Handcrafted metrics, they're simple, they're super computationally efficient, but they require a lot of trial and error to come up with one. And finally, more recently becoming more and more popular is the D-feature spaces. They kind of built on this idea that when we take a neural network that has been trained on some computer vision task mimicking humans, like object detection or image classification, it ends up learning features that are very perceptually uniform, and they kind of translate well to image quality. For example, LPIPs, DIST, and PIAP use 2D CNNs that have been trained on prior classification tasks, and they just work very well on image quality data sets. Since they work so well on image quality data sets, it was a natural question we asked that if 2D CNNs capture spatial artifacts, 3D CNN should capture spatiotemporal artifacts. And surprisingly, this area was very underexplored for videos. So we decided to go in this direction of using D-feature spaces of 3D CNNs. So let's see how we can define a quality metric using a pre-trained 3D CNN, and then we can explore different network architecture designs and training methods and such. So what we do is we take some 3D CNN, we can train it on some classification task. It could be action recognition or video classification, and then we freeze the weights. We do not change the weights at all. These weights do not see video quality data sets. Then we pass both the distorted and distorted and reference videos through this network, take out the internal activations, find the L2 difference between the reference and distorted features, then weigh every channel separately, differently, using learned weights. I'll come to it in a moment. And then just average it out using mean pooling to get the final video quality. Now, every channel kind of learns a different feature. It could be blurring, could be flicker, could be ghosting. So every channel is differently important to the final quality. And that's why we need to weigh them differently, and hence we scale each channel differently. Note that there's just like around 1,000 channels, so only around 1,000 free parameters, which is different from 12 million free parameters of the network, which we do not train. So we do not overfit on the data sets. All right, so with this, the previous architecture, we tested different configurations. We tried 2 different 3D CNNs, ResNet 18 and C3D network, which have been trained on action recognition and video classification data sets. Then to learn the calibrate the channel scales, we used 3 video quality data sets. Gaming video set, which is video game videos with H.264 compression, live stream, which is natural streaming videos, and CGVQD, which I described earlier. And we had some interesting observations. Different 3D CNNs perform very differently. 3D ResNet 18 outperformed C3D network very significantly. So it's important what kind of a 3D CNN network you use. We also tested 3 different types of convolution techniques, vanilla 3D convolutions, then factorized 3D convolutions, which is basically 2D CNN followed, 2D convolution followed by 1D convolution in time, and mixture of 2D convolution and 3D convolution. Surprisingly, it did not have much effect on the metric performance. And we also noticed that pre-training on computer vision data sets and calibrating on video quality data sets both have a significant effect on metric performance. The most interesting finding in this was even when we do not calibrate this metric on any video quality data set, basically it's just pre-trained on action recognition, it still outperformed or at least performs similarly to existing traditional metrics, which is amazing because this kind of means that 3D CNN features are very perceptually uniform, and hence the metric should be built using them. So here's, we take out some of the best configurations from our experiment and define a CGVQM metric, which we release open source after this talk. So the definition of CGVQM5 is we use 3D ResNet 18, we take the 5 layers out of it, we use R3D, vanilla 3D convolutions. It's calibrated on 20% of gaming video set, live stream set, and CGVQD. And the metric outputs values in the CGVQD scale, which is the perceptually meaningful scale of very annoying distortions, slightly annoying distortions, or imperceptible distortions. We also have a lightweight 2-layer variant of CGVQM, which performs slightly worse than CGVQM5 in terms of correlation with human ratings, but it is more computationally efficient. Here's the same plot I showed earlier with CGVQM5 results. The last 2 ones are us, and we tested it on 3 different statistics: Pearson correlation, Kendall correlation, and root mean square error. And as you can see, we have kind of bridged the gap. We are still not human level, but I think it's an important step forward from the last best performing metric. So we went from 0.78 PLCC to 0.87 PLCC. And to make sure that we are not just performing well on the data sets we tested, we also tested on 6 more data sets, which we did not train at all. Together, the 9 data sets contain natural and synthetic videos, modern and traditional artifacts, all sorts of viewing conditions, display devices, and such. And again, we consistently kind of performed in the top 25% of all performing metrics across the metrics we tested, outperforming, again, popular metrics like color video VDP, LPIPs, and VMAF. Sorry for so many numbers. Just the last line is interesting. Another very important advantage of a metric is that it doesn't just give you a video quality score for the entire video. It tells you where the errors are and how much the error is. To evaluate how well we were doing on error localization, we used the LockWiz dataset, which is basically 300 images marked by 16 participants each, giving us like probability of detecting errors on every pixel. These are the human marking maps. Then we tested multiple metrics as a binary classifier, whether there's error on this pixel or not. and we used receiver operating characteristic curve and Mathew correlations for this experiment. And again, we outperformed most of the popular error map generating metrics like LPIPs, color video VDP, foveated video VDP, and SSIM. Here's an example error map from our data set and the metric combination. You can see that the metric kind of highlights ghosting in bright regions like car lights and street lamps, and downweighs the same ghosting in car shadows, which is less visible. So is finally the video quality assessment problem solved? Far from it. We still have a long way to go. One of the major problems we noticed in CGVQM was that we are using uniform mean pooling strategy. But the problem is when you have highly localized distortions. For example, in this scene, most of the distortion is on the small red particles you see floating around. There's ghosting on it. But since they only contain very small area of the video, in the final average pooling, they have very little influence on the final quality. So what the metric ends up doing to match human rating, it ends up amplifying errors all across the video, which is obviously suboptimal and not perceptually accurate. We need better saliency-based or attention-based pooling methods, which kind of just focuses on regions of interest. Again, we currently do not have any way to adapt to different viewing configurations. Operating in photometric units might solve that. We only explored training on sports data sets because they were available. But maybe if we pre-train it on synthetic data sets, the learned perceptual features would be even better. Some artifacts are less visible when the objects are really fast moving, but we do not model that. Maybe incorporating optical flow can improve the metric. And our data set is kind of small, just 80 videos. But we were kind of motivated by identifying which areas require further investigation. So what we found out was that variable rate shading, all the metrics kind of agree a lot, probably because the artifacts in VRS are very similar to compression artifacts, while rendering techniques like Gaussian splatting and neural frame interpolation had a huge disagreement between metrics, which means we require further investigation in this direction. And this is the biggest problem we are facing. Full reference metric are great, but they're not super practical. When you want to test your techniques in the wild, reference is rarely available. So we are kind of working on no reference alternatives for this metric. So let's wrap it up. Here are the key takeaways from this talk. Current metrics and video quality data sets do not model spatiotemporal graphics distortions. We introduced a new data set that is built using 6 modern rendering techniques and 14 different scenes. We introduced a new 3D CNN-based video quality metric that can model spatiotemporal artifacts, produces both global scores and localized error maps. It is shown to outperform existing metrics on multiple data sets across different domains. Looking ahead, we want smarter pooling strategies, display adaptive nature of the metric, and we want to work towards no reference video quality assessment, especially for generative pipelines. You can access the source code by scanning this QR code. Thank you.
Thank you for this very interesting talk. We are running a bit late, but we have time for 1 or 2 questions. Anybody? Yeah.
That was really neat work. I think we'll probably use it ourselves. So, do you think that if you use non-experts as your measurement, your stuff would actually be better than is implied by your graphs, because graphics experts are so picky?
Could be. We found a huge consistency between all the, maybe I have a backup slide for that, huge consistency between different participants. And like level of expertise kind of varies between participants, right? And even then we had huge consistency. So I'm assumed that the findings will carry over to non-experts too.
Thanks.
Yeah.
Okay, maybe one more quick question.
Do you want to explain a little bit more about the non-monotonic trends that you saw? The only thing I'll mention is the perception distortion trade-off. I'm not sure if you've come across that previously.
Right.
Yeah.
Do you mean the perception distortion trade-off paper?
Exactly.
And
So
using the metric as a loss function and it doesn't work kind of thing?
yeah, exactly. The fact that if you minimize distortion, it actually doesn't maximize perceptual quality.
Yes. Again, it's an open problem, and I guess this metric lies in the. It's a distortion metric, not the traditional perception metric in the sense that which compares distributions, quality distribution. So again, referring to that paper, perception distortion trade-off paper, maybe you can use this as a loss function as long as you define that this is acceptable amount of error, and then you can use GAN-based methods or KL divergence to navigate the trade-off curve. But yeah, we haven't explored that. It's fully differentiable. You can use it as a loss function, but it's based on 3D CNNs, which are not super efficient. So you have to find the sweet spot between training and
Thanks.
quality.
Okay, great. Let's thank our speaker again.